Module 4 Investigation 10, Pennies Activity, Rate of Change for Exponential Functions. Exponential functions have a special relationship to their rate of change that no other type of function exhibits. We will reveal the nature of this special relationship by considering pennies being stacked on the squares of a chessboard. Suppose 2 pennies were placed on the first square of the board, 4 pennies on the second square, 8 pennies on the third square, and 16 pennies on the fourth square, etc. We will explore the average rate of change of the number of pennies per square as we move forward 2 squares at a time. 1a. Define a function that determines the number of pennies on a square in terms of the square number. So I want to let n be the number of pennies on a square and let s be the square number. And I want a function that determines the number of pennies. So I want the number of pennies in terms of the square number. So I want f as a function of s. So let's see, since I'm doubling, I think this is an exponential function. The number of pennies on the initial square is 2. And what's my growth rate? See, we double each time, so we always multiply the number of pennies by 2. So note, I think this equation works if we're on the first. Nope, it doesn't quite work. Let's subtract 1 here. Because if I'm on the first square, 2 times 2, there's a, let's see, s is 1 minus 1. 2 times 2 to the 0, that's 2 times 1 equals 2. That's right. If I look at what happens on the second square, 2 times 2, 2 minus 1 is 2 times 2 to the first, or 2 times 2, which is 4. That's correct. And then if I just multiply by another 2, I'll get 8 and then 16, etc. So this function works. I just checked the book and they have an even simpler formula. It's kind of a simplification of ours. Remember the laws of exponents. If you have, let's see, this is an exponent of 1, the same base multiplied together in 2 different exponents, you add the exponents. 1 plus s minus 1 is just s. So we could have defined our formula to be simply 2 to the s. Fill in the following table by finding the average rate of change of the number of pennies per square over 2 squares. Report your calculations using improper fractions first, not decimals, then simplify your result if appropriate. So from here to here, what's the average rate of change? Remember, the average rate of change is the change in the output over the change in the input. Here the change in output is 6, the change in input is 2, so the average rate of change is 6 over 2, or 3. For the next one, again, the change in input is 2. For each of these, the change in input is 2, and here the change in output, 32 minus 8, is 24. So 24 over 2. 12. Here the change in output, 128 minus 32 is 96. So 96 over 2 is 48. The next one, 512 minus 128, that is 384, so 384 over 2 gives us 192. And let's see, this one, the change is 1536 over 2 is 768. And the last one, the change here is 6,144. Divide that by the change in the input of 2, and we get 3,072. Part C, choose one of the average rate of change values that you found in the table above and explain in words the meaning of this average rate using the context of the problem. So I'll take the first one, the average rate of change of 3. So let's think about that in terms of the square and the number of pennies. On the first square, we had 2 pennies. And then on the second square, we had 4 pennies. And on the third square, we had 16. So this is square 1, 2, 3. Okay, and then we saw that if we look at the change in the number of pennies over the change in the square, from 1 to 3 square, so 3 minus 1 here and 16 minus 2 here, we got 14 over 2. That doesn't seem right. Nope, that's not right, because square 3 we just had 8 pennies. Sorry about that. Oops. Okay, 8 minus 2, 6 over 2 is 3. So notice that when the input changed by 2, the output changed by 6. But what this average rate of change means, it's the constant rate that we could achieve the same change in output with the same change in input. Now, talking about it in terms of pennies, it kind of makes more sense. What that 3 is saying is if we had our squares, if we want to get a change of 6 from 1 to 3, we could instead of increasing exponentially, we could increase linearly. We could add 3 here to make this 5, add another 3 to make this 8. Then notice that the change in pennies over the change in the square is 8 minus 2 over 3 minus 1 is 6 over 2, which is 3. So here we just added 3 pennies each time. Here we added 2 pennies, then added 4 pennies. That's exponential growth. This is linear growth. The constant rate of change basically tells you the linear growth factor you would need to have the same change in output over the same change in input. That's our average rate of change. Part D, focus on the average rate of change column. As you move down the column, what do you notice about the pattern of these values? Hint, think about the notion of repeated multiplication that we previously explored. So here's our average rate of change column. once again, the question, focus on the average rate of change column. As you move down the column, what do you notice about the pattern of these values? Let's see. I think I noticed something. We multiply by 4 to get to each new value. That tells me that we have exponential growth. 4 is the 2, is it the 2 unit or the 1 unit? I'm not sure exactly how we can say this, but 4 is a growth factor of sorts. Let's see. Yep, so the average rate of change exhibits exponential growth, just like the number of pennies exhibits exponential growth as well. And I'm pretty sure this is the 4 is the 2 unit growth factor because the squares were increasing by 2. So it appears that the 1 unit growth factor would be 2, the square root of 4, which is the same as the growth factor for the number of pennies. Oops. Wait a second. Yeah, so these are increasing by 4 because that's our 2 unit growth factor. But if we go back to our original situation, the growth factor was 2 because for each, that's the 1 unit growth factor. For each square, we double. So, what do you notice about the pattern of these values? So there's a growth factor of 4. Each average rate of change is 4 times the previous one. And again, because we were looking at a change in input of 2, that's the 2 unit growth factor. The next question we'll get at the 1 unit growth factor, I think, or maybe that's in part F. Let's take a look at part E. Now let's focus on the relationship between the number of pennies and the average rates of change. What do you notice as you compare the average rate of change on each interval with the number of pennies on the square at the beginning of that interval? Based on your observation, what relationship exists between the number of pennies on a square and the corresponding average rate of change as one advances forward 2 squares? Okay, so I'll just read this problem again one more time. What do you notice as you compare the average rate of change on each interval with the number of pennies on the square of the beginning of that interval? So here's an interval. The number of pennies was 1. And so our average rate of change was 3. Here on the next interval, the average rate of change is 12, and our initial input was 3. So do we notice any pattern I don't really see a pattern. So here's initial number of wait, maybe I'm looking at the wrong thing. What do you notice as you compare the average rate change on each interval with the number of pennies on the square at the beginning of the interval? So the number of pennies 2 with 3, and the number of pennies 8 with 12, the number of pennies 32 with 48. Let's see, 3 divided by 2 is 1.5. 12 divided by 8, let's see, that's the same as 3 divided by 2 is 1.5. 48 divided by 32, that's also 1.5. So there's actually a proportional relationship here between the number of pennies on the square and the average rate of change. So the average rate of change is 1.5 times as large as the initial number of pennies when advancing 2 squares. The average rate of change is proportional to the number of pennies. Now that you know what type of relationship exists between the number of pennies and the corresponding average rate of change, what other facts can you conclude about this relationship? So we know there's a proportional relationship. That means that the average rate of change multiplied by, depending on what our unit of increase is. In our case, the unit of increase was 2, and so then we multiply by 1.5, but in general there's going to be something different, some number k. Average rate of change multiplied by k results in, let's see, the number of pennies. Really, we looked at it the other way. It was the number of pennies multiplied by 1.5, or j, results in the average rate of change. The book lists a lot of other things, basically just going over the idea of proportionality. Scaling the number of pennies by some factor should scale the average rate by the same factor. A graph of the average rate versus the number of pennies would be a straight line going through the origin. That's because there's a proportional relationship. It defines a linear function. Let's see, if the number of pennies were 0, the rate would be 0. Fixed changes in the number of pennies will correspond to the same amount of change in the average rate. So if we just go back and look at this table again for a second, I'm interested in, what if we made the table just by ones? Then for every corresponding change of 1, the average rate of change of the pennies would be 2. To me, that's interesting. The average rate of change of the pennies is the same as the growth factor. And that's really what I took away from this lecture. Or sorry, not quite. It's the growth factor of the average rate of change is the same as the growth factor for the number of pennies.